It's certainly a pleasure to be here, and I'm delighted to be in this august company. I wanted to speak a little bit about Menachem before I got into the mathematics. And most the microphone isn't working. What is? Did you? Oh, for the video. Okay. No, I didn't understand. I thought the microphone would project my voice to the audience, but if it's not going to do the job, I will do the job. So I wanted to start with the fact that Menachem Magidor officially received his doctorate in 1973, but he told me yesterday the work was done in 72. That's the point he thinks of himself as having been done. And that made me think of Baumgartner, my advisor, who came to Dartmouth College without the doctorate in hand, as expected, because his advisor made him rewrite it. Hebrew University asked Menachem to translate his work into Hebrew, but then they couldn't find referees for it, not enough, so they asked for an English version too. And here we have his advisor, who I was really delighted to see at this conference, and that was something very nice for me. This is my first memory of Menachem. I think it was in 1973. It was certainly in Berkeley. I think there's probably a lovely story behind the picture I have there. I was just looking for a picture where he had the darker hair, because that's what I do remember. But what I really remember about that particular meeting was Sarah making falafel, which I had never eaten before and didn't eat for years after that. So there was this mysterious food that I thought was very delicious. And maybe we can ask Menachem what this picture is from in the future. So next up, he's been at Hebrew University most of his career. He was promoted to associate professor in 1978, to professor in 1982. We've already heard about his tenure as president, and I thought we should have an official picture with a tie for what I think of as the suit era. I was very happy that he would be visiting lots of us all over the world in connection with his duties as president. He would make stops and say hello, and that was really wonderful for me. And there were a lot of beautiful suits too. So this is the list of Menachem students from the Math Genealogy project. And maybe there are some students that should be on here that are not, almost surely. So this is a heads up to an advisor that it would be really nice for the rest of the world if those students, when they got their degrees, got put on the list. And somebody has to do it, and the advisor is the ideal person to do that. So I would like anybody that is a student of Menachem, whether who has gotten the PhD or is currently a student, to stand. An excuse to stand. Come on, guys. Yeah. Okay, so thank you very much. And next, this is, here are some of the co-authors. So I just went to MathSciNet and I just snatched all the co-authors that they listed, and then I formatted it, and it even came out in even columns, which was lovely, especially as I had a predetermined form I was using. So how about people who are co-authors, not just on the Math Silas, because I know there are a lot more. Some of the papers maybe haven't been published. So I would like you to have an excuse to stand up. Come on, guys. It feels good to stand up. So this is really wonderful. Hey, yeah, why don't you stand up too? Come on, be part of this wonderful group. This is a very collaborative group, and I'm happy that all of you are here today, and there are lots who could be. And there's another aspect of Menachem's service to the greater professional community, and that's that he has been involved in organizing conferences, making sure there's money for conferences, along with lots of other people in this room. And I think that is a wonderful service that we maybe honor briefly at the end of a conference, but seeing people do that over a long period of years is something that I think really deserves good attention. And now we're going to move the conversation to mathematics. You can see this is a very social subject, and we're about to go away from the pictures and into the text. So I'd like to talk about a series of theorems and generalizations or shift of context. And the one I'm starting with is the Balance-Baumgartner-Heindltodorovic theorem, which is from 1993. It says for every regular uncountable cardinal kappa and every xi less than kappa and k less than omega, if you look at 2 to the kappa plus, you take the pairs from 2 to the kappa plus, you color them with k colors, then there will be a color, all of whose pairs are that color, and for a whole set of size kappa plus psi. It's got a beautiful proof using ideals that come from chains of elementary submodels. And the order type kappa plus psi, yes. Pairs from the set of order type kappa plus psi, all that one color. Ari Brodsky, who's here today, has a balanced Baumgartner-Heindltodorovic type theorem for trees. For every infinite regular cardinal kappa and xi with 2 to the cardinality of xi less than kappa and k less than omega, if you take a non-2 to the less than kappa special tree and you split its pairs into k color classes, you can find a subset of order type kappa plus xi, all of whose pairs get the same color. And Brodsky developed a theory of stationary subsets of trees in order to prove this theorem, and also used ideals that come from chains of elementary submodels. So he generalized the way one can look at stationary subsets of trees, which was, I thought, a very nice theorem. The next item I'm looking at is a theorem of Paul Erdős and Richard Rado from 1956, the famous 56 paper. And in this paper, they showed that the continuum hypothesis implies the polarized partition relation, that if you have alpha 1 over omega and you take, so you're looking at colorings of pairs from the Cartesian product of alpha 1 with omega, and you're just looking at them, you're coloring them with 2 colors. There's a way to do it so that you can't get a subset of the first part, a subset A of the alpha 1 and a subset B of omega of the full sizes so that it's constant. You can kill that one off. So this is a polarized partition relation. There are lots of different ways of looking at them. They turn out to be quite interesting. More recently, Shimon Garti and Sauron Shayla proved that it's consistent with ZFC that all cardinals theta with alpha 1 less or equal to theta less or equal to the continuum have the positive partition relation that looks like that, where we've replaced the alpha 1 from the previous non-arrow theorem with this theta between alpha 1 and alpha 2. Earlier, they had shown that the partition relation was true for theta less than s, the splitting number, and here they show it's true for r less than theta, the reaping number, and their model has alpha 1 equal r, less than or equal to s equal alpha 2 equals c, and So they use these cardinal characteristics in their proof. And the question that they had, is it consistent that the reaping number is less than the splitting number and the continuum is bigger than Aleph 2? Now I'm turning to topological partitions, and the first item I'm looking at is reduction of colors. I put this one first among the topological ones because it was Claribet Pina talking in Barcelona at a lovely meeting a few years ago, the European Set Theory Society, I think that was. She's investigated the minimum number of colors needed when you're doing partition relations and you're trying to shrink the colors down. If you just take finitely many colors, can you reduce the number down? And she has proven that for arbitrary colorings with at least 2 colors, if you have omega to the omega and you look at it as an ordinal topological space and put the topology on based on the ordering, as we heard earlier in a talk, then if you color the pairs with some arbitrary finite number of colors, there is a way to shrink down to at most 6 and still have a copy of omega squared plus 1, a topological copy. That means it's homeomorphic to that. It doesn't have to be order isomorphic to that. That uses at most 6 colors. On the other hand, if you color it with 9 colors, there's a way to color omega to the omega, the pairs of omega to omega with 9 colors, so that you can't shrink to a subset homeomorphic to omega squared plus 1 that only uses 5 colors. You're stuck. So that's a lovely simple theorem on one of my favorite ordinals. And now I'll look at the topological pigeonhole principle. So Eric Milner and Richard Rado came up. Yes?
Why do you go from 9 to 5?
The general coloring has 9, and you try to shrink. You can't shrink to 5. You can shrink to 6, but you can't shrink to 5.
If you had 8 colors, you could imagine that you could shrink.
This is her counterexample. Okay, this is her counter. Yeah. Eric Milner and Richard Rado came up with a pigeonhole principle for ordinals. And Jacob Hilton, the student of John Truss at Leeds, has developed a pigeonhole principle for ordinal topological spaces. So here you're coloring ones, singletons, or the points. And to do this for absolutely everything, he went around and found lots of other people's work, including that of Bill Weiss, Carl Prickry, Solovay, Shayla, and there are consistency things in the middle of this for certain cases. I'm just giving you a small slice of it. The whole topological pigeonhole principle takes more than a page of text to write out all the cases that he uses. So, okay, so here are the 2 results that he said were his main contribution. And you see these sharps up here? Is that what you're talking about?
What do you mean by P?
Oh, P-top is the smallest ordinal, or smallest size of the of an ordinal, so that if you're trying to take a coloring into this many pieces, so K pieces, you have a partition into K pieces, and you know what size you want for each of the colors. That's what this is, right? This is the smallest one, so that if you have that many and you do the splitting, one of them will have a big enough piece.
You mean the minimal size one?
This is the minimal size, yeah. Okay, so that was a good question because it helped to have everyone understand what the p-top is, and it also helps people to know what the p-ord is. In p-ord, all you're caring about is the order type of the set, but in p-top, all you care about is the homeomorphism type of the set. And those two things can be quite different. And what he showed is that if you have ordinals alpha 1 through alpha k, and you look at those omega powers, the successors of those omega powers, then the value of p-top can be expressed using the natural sum or the Hessenberg sum, whose definition is up here. And if you're looking at not the successors of those ordinal powers, but just those ordinal powers, then you can get the omega to the p-ord, the ordinal version, the ordinal pigeonhole principle value that you get. So those are two very nice expressions. They deal with some of the most interesting cases where you get a nice answer. This theorem that he has encompasses everything from the finite case up into things with multiple copies of omega 1. So now I'm moving to another part of topological Ramsey theory. And this is work by Andres Caicedo and Jacob Hilton in their search for Ramsey numbers for ordinal spaces. So in some sense, the p-top was like a Ramsey number because it was the smallest value for which you got the smallest size resource where you got the kind of thing you were looking for. You can look for Ramsey numbers for pairs or other sizes of things that when you're coloring something other than singletons. And Caicedo and Hilton looked at pairs, coloring pairs. They also looked at the pigeonhole principle, and they were interested in two flavors of goals, where in the pigeonhole principle for topological spaces, you were just looking at things that were homeomorphic to the given space that you were listing, the ordinal space. Here they also looked at spaces in which they wanted to have an order type, and they wanted to have it closed in its supremum. So that's on the next page. So our top of a sequence of ordinals alpha I is going to be the topological Ramsey number, namely the least beta, such that beta is big enough to give you a positive partition relation for pairs for that particular sequence. Our closed a sequence of ordinals alpha I is the closed Ramsey number, namely the least ordinal beta, such that if you start with beta and you color the pairs from beta, you will get a copy of alpha I, which is of that order type and closed in its supremum. So this is not the first time such things have been looked at. Erdős and Milner, well, because Baumgartner looked at it, Bill Weiss looked at it, they were among the earliest. Go back. It didn't say that it was order isomorphic, right? Go back.
I don't understand the difference between topological and closed. I mean, isn't closed something for
It's an ordinal. It's an ordinal. So you have a subset of an ordinal. If you have a sequence of ordinals going up to a limit, it's closed if that limit point is in there too. If you're looking for something that's homeomorphic, you need your limit points, right? If you don't have the +1 on the end, then you don't necessarily have to be closed along the way. So Erdős and Milner had a theorem early on. I think maybe it was when Milner was in Singapore that he really started working on this particular problem. But it says that if you look at a power of omega, omega to the alpha, and you look at colorings into two color classes, if you can get omega to the 1 plus beta in one class or k in the other, then you can pump it up and show that omega to the omega to the alpha plus beta will arrow omega to the 1 plus beta, but now you have 2k instead of k. So you can pump the finite part. Andres Caicedo and Jacob Hilton found a counterpart which they call the weak topological Erdős-Milner theorem. Let alpha and beta be positive, countable, non-zero ordinals, and let k greater than 1 be a positive integer. If omega to the alpha topologically arrows omega to the beta k upper 2, then if you increase that upper exponent, i.e. if you look at omega to the alpha times beta, then that will give you the desired partition relation for omega to the beta and k plus 1. So you're making a much bigger resource for a significantly smaller increase in your finite set, but at least you have some way to push up the resource in a way that keeps you in the countable ordinals and a way to pump up the finite set. In a corollary to their main theorem, proved that these Ramsey numbers coincide in certain cases, the closed ones and the topological ones, and give upper bounds for them. I didn't give everything here, but as I noted before, the number you need is always countable if you want one of these topological partition relations for a countable ordinal and a finite alternative. And then they have a couple more, which I think I will not look at too closely. And their questions were, is there a topological partition ordinal, alpha greater than omega? That is there an alpha greater than omega so that alpha is big enough that whenever you color its pairs with two colors, either there's a copy of the same ordinal alpha or there's a triangle in the other color. And the other question they had was, is it possible to reduce the computation of the topological Ramsey number for alpha and k to a finite combinatorial problem, even for small alpha, even for alpha less than omega squared? And now I'm shifting to the Halpern Likely theorem. You see up here some trees with some jig-jags in them. These are illustrations of a k-dense subset and a kx-dense subset, the difference being taking the x and then shrinking to its successors, whereas here you're going above everything on the kth level. This is from Todorovic's wonderful Ramsey theory book, and it explains one of the critical, well, it's a pictorial representation of a critical aspect of the Halpern Likely theorem, which uses k-dense matrices and kx-dense matrices because they're looking at products of trees, and you want to look at something that's a product of some nice things inside to get a nice combinatorial result. So I thought that was the easiest way to give an impression of that. And here is an asymmetric version of the Halpern Likely theorem for every coloring of the finite product of finitely branching trees. So that's the pi I less than d. Ti is split into two color classes, K0 and K1 in this case. Either K0 contains a K-dense matrix for every integer K, or, so that's a product of these simple things, or there is some vector x in the product such that K1 contains a Kx-dense matrix for every, oh, I didn't get all the typos, integer K. So this is a very lovely theorem. It's used to prove a lot of different things. There are many generalizations of it. And what I mainly wanted to bring to your attention, that Laver's conjecture is still open for every level set coloring of the infinite product of downwards closed perfect trees with two colors. There is some j less than 2 and some x in the product, such that for every k less than omega, kj contains a Kx-dense level set matrix. So this is saying you can do it, but now you're working with infinitely many trees. Before you were only working with finite product. This is trying to do it for infinitely many trees. Now I'm turning to joint work with Shimona and Mitchell, but the starting point is a theorem of Dennis Devlin, a student of Jim Baumgartner, who proved that if you look at the rationals and you look at n-tuples from the rationals and you split them into finitely many pieces, you can find a copy of the rationals which uses only tangent number many colors, but there is a coloring so that, but you can't shrink further, I guess. Let's just put it that way. So for regular cardinals kappa, there's a natural order less than or equal to q, extending lexicographic order on kappa into 2, so that q kappa, the set of sequences of length less than kappa, binary sequences of length less than kappa, and less than or equal to q, is a kappa-dense linear order. This is the generalization of the rational numbers. Mirna Shimona, Bill Mitchell, and myself proved that for every positive integer m, there is a number t plus sub m, finite, such that for any cardinal kappa, which is measurable after generically adding lambda many Cohen subsets of kappa, where lambda satisfies the partition relation, that if you color the two m element subsets of lambda with 2 to the kappa colors, you can find a subset kappa which is monochromatic. Then the kappa-dense linear order q kappa satisfies the same type of partition relation that we had for the rationals, that there is a way to shrink the number, reduce the colors to this Tm plus, but you can't reduce it further. And the Tm plus is the cardinality of a set of finite trees, and the number of those finite trees grows pretty fast. A key tool is the theorem of Sauron Shayla that is a generalization of the Halpern Likely theorem. That's how he describes it. Suppose that m is less than omega and kappa is a cardinal which is measurable in the generic extension obtained by adding lambda Cohen subsets of kappa, where lambda satisfies the partition relation given in the statement of the theorem. Then for any coloring D of the m elements antichains of the set of sequences of binary sequences of length less than kappa into sigma, namely sigma fewer than kappa colors, and any well ordering curly less than of the levels of this, this tree, there is a strong embedding E of the sequences of binary sequences of length less than kappa into itself, and a dense set of elements W such that the embedding preserves the curly less than for all S for all S and T from the cone above W, and the coloring D of E of the embedding applied to an A and the coloring D of the embedding applied to A are equal for all curly less than similar M element antichains A and B from the cone above B. So it's a nice uniformization theorem. Based on work of Heinl and Komjat, the positive partition relation for Q kappa does not follow from any large cardinal hypothesis on kappa, because they've shown that there is a forcing of size aleph 1, which adds an order type theta of size aleph 1 with the property that for every order type psi fails to satisfy this square bracket partition relation regardless of the size of psi. So you just can't. So this square bracket one would say you could throw away a color, but you can't throw away a color. There's a coloring of the pairs with omega 1 colors, and you can't omit any colors on subsets of this order type. Komjat was really startled when we told us his theorem. He said, no, that can't be true. And then,
It's not an order.
what?
It's a linear order.
I think it's a linear order, the order type. Oh, I thought I got rid of this. Go back.
Yes.
Here.
An order type. Yeah.
For every, yeah, you can't, there's no big order type. Yeah, linear order type. Just nothing works in that model. Our proof uses the theorem of Shayla quoted above to show that all the types we say do occur in every large set. Does the negative part hold for sufficiently large m less than omega for some regular cardinal which is not measurable after generically adding lambda Cohen subsets of kappa where lambda has this special partition property? So the types that you look at and say, hey, here's a finite tree. If you look like this, we're going to color you this kind of a color. You do it according to the types. There are only finitely many of them. Do they survive even if you don't have the power to prove the positive partition relation? So I'm hoping people will be interested in that particular thing. And now I will comment again on the community that we are part of. And I think we have a coffee break so we can continue to engage in conversation and enjoy ourselves. So.
It's historical one. I didn't know the theorem of Komjat and Heinl. From when is it? Which paper?
I can talk to you about that later. Yeah. I might have erased it out of the bibliography. I guess I had more bibliography than I thought. Well, thank you again.
Yeah.